All right, welcome everyone. Let me start by thanking the organizers for the invitation to speak. Uh, I've never participated in this kind of online asynchronous conference before, so I'm very curious to see how this will work, and I look forward very much to the discussion sessions to follow. Today, I'm going to tell you about this paper, Constraints on Long-Range Forces in de Sitter Space, that I put out last year, together with this wonderful group of co-authors, Daniel Bauman, Kurt Hinterbickler, Austin Joyce, Hayden Lee, Xiaji Mei, and Nathan Murrens. And this is quite a technical paper, but I hope that in the next 20 minutes or so, I'll be able to communicate the basic ideas behind the constraints that we derived, and more importantly, what the punchline is, which I think is compelling and possibly even useful. So to explain the motivation behind this work, I want to think about this as a kind of preliminary exercise that you would do before you engage in the more serious business of trying to build models for cosmology. So I come from the world of scattering amplitudes, which is a little bit closer to flat space collider physics. So let me explain the analogous problem there. So suppose you wanted to engineer some model to describe beyond the standard model physics that you could probe in some future collider. So a preliminary exercise before you start engineering quantum fields and Lagrangians and doing all of that is you might just ask, what are all of the consistent free quantum fields that you can have in Minkowski space? So what kind of particles, even in principle, could show up in some future collider experiment that we might want to include in our models? Once you answer that question, you then might ask, well, okay, what are all of the consistent ways that I can make those free particles interact in some weak way, some perturbative way? And it turns out that this problem is essentially solved. We now know all of the constraints, more or less, that weakly interacting quantum fields have to satisfy. There's some lingering questions if you're very ambitious about strongly interacting fields, but let's say, as I'll explain in a second, that this is essentially a solved problem. So in cosmology, we might try and do something similar. I might imagine that we want to build some model that describes some early period of quasi-exponential inflation. And so a preliminary exercise to building those detailed models is I might ask, what are all of the consistent free quantum fields that I can have in de Sitter space? And then I might ask, what are all of the consistent ways that I can make those free quantum fields interact? And surprisingly, we don't know the answer to this second question. And so there are maybe questions lingering about model building and the possibilities for model building that can be resolved with pure theory. So as I said, for flat spacetime, this is essentially a solved problem. And the most powerful constraints of this kind come from an analysis of on-shell scattering amplitudes in the infrared, in the so-called soft limit. And so for a period of many decades, many people contributed to this story. We developed a kind of complete classification of all consistently interacting classical gauge theories. So famously, if you have a massless spin 1 particle, it only makes sense in the context of a Yang-Mills theory based on a classical Lie algebra. If you have a massless spin 3 half particle, that can only make sense in the context of a theory of supergravity, and you can have at most 8 of them. A massless spin 2 is necessarily the graviton and is completely unique, and there are strict no-go theorems that you can derive that say you shouldn't even look for particles with massless particles with spins greater than 2. They don't make sense. So what's surprising to me and motivating to think about this problem is that there's no known classification in de Sitter space. And so this talk and this work is our attempt to try and clean up this subject a little bit. So we want to do something like the scattering amplitude analysis for de Sitter, and so we need a kind of asymptotic observable. So here's a Penrose diagram of de Sitter space. We wanted to find something which sort of lives on the boundary of this spacetime, and that natural boundary is this spatial slice at eta equals 0. Think of it as future infinity. So the object that is sort of closest to a scattering amplitude and is defined on this late time surface is the so-called Bunch-Davies wave function. Formally, you can define this as some path integral over your bulk fields, where you have some initial condition that defines the Bunch-Davies vacuum state, and then some future boundary condition involving some unspecified profile function var phi, which is defined as the coefficient of some part of the mode functions which scale like eta to the d minus delta plus, where d is the spacetime dimension, and delta plus is what we call the dimension of the dual operator, and is defined for scalar fields at least as the largest root of this quadratic polynomial. So one of the most amazing facts about the Bunch-Davies wave function that we'll make heavy use of in this talk is that it has all of the same kinematic properties as the generating functional of local correlation functions in a Euclidean CFT, a conformal field theory. So in this sense, it's a kind of close cousin and analytic continuation of the more familiar story of ADS CFT. This in fact gives a sort of tautological or weak version of the ds-CFT correspondence. The statement is that if you take the Bunch-Davies wave functional, you take functional derivatives with respect to these profile functions, this generates some functions which have the same conformal Ward identities as the correlation functions in a Euclidean conformal field theory, maybe a non-unitary one. This is an analytic continuation of the usual ADS-CFT story. Okay, so let's start by looking at this first question I mentioned, which is to take an account of all of the consistent free field theories in de Sitter space. So as Wigner explained for flat space long ago, this is equivalent to the mathematical problem of classifying the unitary irreducible representations of the isometry group of your spacetime. So for de Sitter, this is some group which is SOD plus 1, comma 1. And the notion of unitarity in this conformal field theory language is equivalent to the statement that the momentum and special conformal generators are Hermitian. And I mention this just to emphasize that this is a different unitarity condition from the one you would normally impose in ADS, and therefore the classification of the unitary irreps in ADS and DS are different. And this is why solving the problem in ADS doesn't automatically solve the problem in DS. Fortunately, this classification was done long ago in the mathematics literature. So today we're going to be interested in the dynamics of symmetric traceless spin S tensor fields. And it's known that the unitary irreps come in three different types: the so-called principal series fields, which are heavy spinning fields, the complementary series, which are light spinning fields. The complementary series fields have a conformal dimension which is bounded above and below. I'll come back to this point later in the talk. The exceptional series fields, which are the symmetric tensor gauge fields, these are the main things we're going to be studying today. So these things actually only exist at certain discrete values of the conformal dimension, d minus 1 plus t, where t is an integer called the depth that takes values between 0 and s minus 1, where s is the spin. For maximal depth, t equals s minus 1, these are just ordinary massless symmetric tensor gauge fields. But for all of the other values of the depth, these are some new objects which have a mass but are still gauge fields and are therefore called partially massless. So the main problem and the reason that we don't know the answer to this classification in de Sitter is that we don't know what all of the consistently interacting gauge theories are that involve these partially massless fields, if any. So here's maybe a more intuitive illustration of these different representations. So on the horizontal, we have the mass in units of the de Sitter length, and on the vertical, we have the spin. And the statement of these principal and complementary series representations is that they live on these continuous blue lines that I've indicated. The claim of the exceptional series is that there's a critical lower bound of these masses, which is called the Higuchi bound, below which the only unitary representations live at these discrete isolated points. These are these partially massless or exceptional series points. So I'm using this notation here where we have spin and depth. So for maximal depth, these are ordinary massless gauge fields, and I've indicated some familiar cases, the photon and the graviton. Okay, maybe a more intuitive and elementary explanation of what the partially massless fields are is to look at the equation for a free massive spin 2 in de Sitter. The statement is that if you tune the mass to some critical value, which defines the Higuchi bound, then these equations develop a scalar gauge symmetry. So this is the gauge symmetry where the parameter is a scalar, which means that 1 degree of freedom is decoupling. So in 4-dimensional de Sitter space, a massive spin 2 field should have 5 propagating degrees of freedom, but at this special mass value, one of them becomes pure gauge and decouples, and you end up with this partially massless spin 2 field that has 4 propagating degrees of freedom. But we don't want to do bulk physics. What we want to do is we want to somehow map this onto a problem in this sort of fictitious conformal field theory that lives at future infinity. And so we need a dictionary between the partially massless fields in the bulk and some conformal primary operators on the boundary. And actually, this was explained long ago in the ADS-CFT literature that the dual operators are spin S tensor primary fields that satisfy an interesting kind of generalized conserved current condition, where instead of taking one divergence of these operators, you have to take S minus T divergences to get 0. This is so-called partial conservation. So I'll use this notation for the rest of the talk where I have x sub s comma t, where s is the spin and t is the depth. And so some familiar examples, a spin 1 field of depth 0 would be an ordinary conserved spin 1 current, and this would be dual in the bulk to a photon or a gluon. A spin 2 depth 1 would be a ordinary conserved spin 2 operator on the boundary, which would be the stress tensor, and its dual field in the bulk is the graviton. A new type of object, for example, would be the 2, 0. This is this partially massless spin 2 field above, and its partial conservation condition is the statement that you have to take divergences on both of its indices to get 0. Okay, so how are we going to bound these things? The idea is to dive into the CFT literature and borrow a strategy that was used to analyze higher spin CFTs by Maldacen and Zhiboyedov in this paper from about 15 years ago. So the idea is that we take these partially conserved current operators and we form topological surface or charge operators by taking S minus T minus 1 divergences of them. So this is one fewer divergence than you would need to get 0, and then integrating the result against some cycle sigma. So these define some topological operators which you can insert in correlation functions with other local operators. And in particular, you might choose a cycle that links all of the local operator insertions and then evaluate it in two ways. One way is you might shrink it down so that it acts locally on each of the local operator insertions. And the other way is that you might close it on the other side of the sphere. The sphere is like the conformal compactification of this spatial slice at the end of de Sitter. And so closing it on the other side of the sphere, you're measuring the charge of the vacuum, which I'm going to assume is 0. So this is the same as the assumption that the gauge fields in the bulk are in a Coulomb-like phase and not in a Higgs phase. So these two facts together give you some interesting global Ward identity or sum rule that has to be satisfied by any consistent theory. Okay, so to proceed, since we don't know the way the charges can act on local operators, we're going to form an ansatz where we have local operators which are formed by linear combinations of primaries and descendants being derivatives of primary operators with some a priori unknown coefficients Cij, which in turn come from the 3-point functions in the bulk. So think of theCijs as like cubic couplings in the bulk. So this becomes especially powerful when we insert them into 3-point functions, because now we get some identity where the C's appear both in the ansatz of the action of the charge operators and also inside of the remaining 3-point functions. And so this gives you some sort of interesting quadratic sum rule on the cubic couplings of the theory, which you can extract by taking this identity and sampling it at random kinematic points. So any consistent conformal field theory, and therefore any consistent bulk gauge theory, has to satisfy these constraints. And so we can really use them to constrain the space of consistent theories. So let's look at some familiar examples. So probably the most elementary example is to imagine you have a massless spin 1 particle in the bulk and some scalar matter fields, which I'll call OI. And I'll assume these matter fields, these scalar fields, have some cubic self-interaction with a non-zero cubic coupling lambda 1, 2, 3. From the massless spin 1 field, I have a dual operator, x1, 0, from which I can form a charge, q1, 0, and I want to postulate some action of this thing on the local scalar operators. And so I'm just going to assert that the only consistent way that this can act is to multiply the operator by a dimensionless C number that I'll call q sub I. So if you insert this ansatz into a 3-point correlation function, then what you get is some rule like this, where I'm going to assume that this 3-point function of the O's is non-zero. And so the constraint that I learn is that Q1 plus Q2 plus Q3 must sum up to 0. So what's the bulk interpretation of this constraint? Well, the bulk field was a massless spin 1. The massless spin 1 field coupled to the scalar fields is secretly the model I'm describing is scalar QED, where these are some electrically charged scalar operators. And these little q's are nothing other than the electric charges of the particles. And so what we've rediscovered is in fact electric charge conservation, the statement that all of the electric charges leaving the diagram have to sum up to 0. A similar elementary example is to consider a massless spin 2 field in the bulk coupled to scalar fields again. And so I'm just going to assert in this case that the unique way that the charge can act on the operators is with a derivative d mu times a number, which I'll call kappa sub I. If I insert this inside of a 3-point function, then what I get is some sum rule that looks like this. And here, the only way that this can be satisfied non-trivially is if all of these kappas are equal to each other. And so that's the statement that this massless spin 2 field is coupling to the scalar fields with uniform strength. So what I've in fact rediscovered is that this massless spin 2 field is a graviton, and that the graviton is constrained by the Einstein equivalence principle to couple to all other fields with a uniform strength proportional to G Newton. So now we want to use these kind of constraints and apply them to cases where we don't know the answer, which are these partially massless fields. So our strategy is actually going to be to look at two of these kind of charge conservation sum rules, which by virtue of the equivalence principle and the fact that gravity couples to everything universally, must have a non-trivial cancellation to be satisfied. So these are the two sum rules. The statement is that of all the operators that you can exchange, they must contain a non-zero contribution from the stress tensor, or in the bulk, this would be non-zero contribution from the graviton. And so these constraints can genuinely fail, and you can prove no-go theorems, which say that partially massless fields can or cannot be consistently coupled to Einstein gravity. So we're going to proceed in a kind of algorithmic way. We'll assume an initial spectrum of operators that consists of at least the stress tensor and one of these partially conserved currents, which means at least the graviton and one partially massless gauge field. We're then going to construct an ansatz for the most general action of the associated charges on these fields. And I'm just going to assert that there are, in fact, finitely many things that can consistently appear on the right-hand side of these relations. We'll then construct the most generally conformally invariant three-point functions involving the operators that we've assumed. We write down these non-trivial charge conservation constraints. This gives us some equations where we sample random kinematic points and gives us a big system of quadratic equations in the OPE or cubic coupling coefficients of the theory, and then we try and solve them. If there is no solution to those constraints, then a model with the assumed spectrum is rigorously excluded. Okay, let's look at the simplest non-trivial example, which is a graviton coupled to a partially massless spin 2. So I'm going to assert that the maximally general form of the action of the charges on these operators is of this form, where the only operators that can consistently appear on the right-hand side is a spin 3 depth 0, a spin 3 depth 1, and what I'll call a spin 2 depth -1. This just means that it's an ordinary field that's in the complementary or principal series, where its dimension is determined by the same formula as the dimensions for the exceptional series with depth -1, but it's not conserved. So we analyze the constraints from those non-trivial identities in dimensions 3 through 7. So this is boundary dimensions. This means to sit at 4 through 8. And if you don't add any of these additional operators and you just have the minimal spectrum of the graviton and the partially massless field, then it's straightforward to show that there's in fact no consistent way to satisfy these constraints. And so you have a strict no-go theorem for all dimensions. In dimension 3, so this would be de Sitter 4, so this would be the most relevant to our world. To make the theory consistent, if you add other operators, you find that you can make it mathematically consistent if you add any two of the additional operators. But in de Sitter 4, which would be 3 dimensions on the boundary, the operator 2 minus 1 is in fact marginally excluded by the complementary series unitarity bound. It sits at right at one end of the range of allowed values, but it's a strict inequality. So it's marginally non-unitary. And so in fact, the only consistent unitary spectrum that you could plausibly have involves the spin 3 depth 0 and the spin 3 depth 1. In higher dimensions, you're a little bit more free. Now the 2 minus 1 becomes a unitary representation. The complementary series bounds are dimension dependent. And so you can satisfy the constraints either by having this guy by itself or both of these things. So as a picture, in de Sitter 4, if you assume that you have initially a graviton and a partially massless spin 2, the only unitary consistent solution is to pick both of these spin 3s. And in higher dimensions, you can have either this guy by itself or both of these. Okay, the second next to minimal case that you might analyze is graviton coupled to a partially massless spin 3 of depth 0. Again, there's a finite ansatz for what can appear on the right-hand side of this relation. Here it's a little bit more complicated. You can go all the way up to spin 5 depth 0, but still there's strictly finitely many coefficients that can appear. We did the same exercise where you analyze these constraints in de Sitter 4 through 8. The minimal theory is again ruled out. In three boundary dimensions or 4 space-time dimensions, to have a consistent solution, in addition to the minimal spectrum of fields, you need either a pair of spin 4 operators of depths -1 and 1, or all three of 2 minus 1, 3 minus 2, and 4, 1. But now you make the same analysis that we did a second ago and realize that these -1 and -2 fields are outside of the unitarity bounds of the complementary series. And so in fact, neither solution is physically acceptable in a unitary theory. And so this gives a rigorous no-go theorem for the 3, 0. But we needed to add this field in the previous example to make the 2, 0 theory work. And so this in turn implies a no-go theorem for the partially massless spin 2. In higher dimensions, this is a little bit less restricted, you can have any two of these fields will solve the problem, and they're all unitary. So this is my final slide. I'll just end with a pictorial summary of the main no-go result of the paper, which is that in de Sitter 4, there are no unitary quantum field theories in de Sitter, which have either a partially massless spin 2 or a partially massless spin 3. Thank you for listening.